In this video, we'll be looking at density, specific gravity, temperature, and energy units. We want to start with density. When we're talking about a material's density, what we're really referring to is that material's mass compared to its volume. It kind of has a basic formula, a basic setup, but this is our first what we would call complex unit, a combination of other units. So we can represent density as density just being an object's mass divided by that object's volume. Some materials that you're very familiar with have a very, very high density. You can think about something like a gold ring or a lead sinker or a coin. There is a lot of mass to that, a lot of weight to that for very little volume. You can contrast that with some other materials that you're very familiar with. Other materials have a very low density. You can think about something like a bag of popcorn. A bag of popcorn doesn't have much mass. It doesn't weigh that much, but it takes up a lot of space. Another thing you're very familiar with a low density would be the air that we're breathing. Not a lot of mass for that air, but it takes up a lot of space. That would give you a very, very low density. What we want to be able to do with density is we want to be able to do problems involving density. The problem I want to do involving density is also a chance for us to practice our dimensional analysis. And I would kind of say that this is kind of the capstone dimensional analysis problem. If you're able to do a dimensional analysis problem that involves density, you know you have it. You have it together. You know you can do any dimensional analysis problem out there. So we kind of want to use this as a capstone. When you're comfortable doing a density dimensional analysis problems, you got it. You understand it, and you're going to be great on all the future ones. So here's the problem we want to do. We're going to take an English density, 6.23 ounces per cup, and we're going to convert it to a metric density, decigrams per milliliter. Now, we'd have some English conversions given to us. We'd have some English to metric conversions given to us. Remember, metric to metric conversions you have to provide for yourselves. You have to come up with that from knowing what those metric prefixes really mean. So we would have some given equalities given to us. 16 ounces in a pound, 2.2 pounds in a kilogram, 946 milliliters in a quart. We'd also have some volume conversions provided for us. 4 cups in a quart, 4 quarts in a gallon, 2 cups in a pint. So we would have the necessary conversions we would need to do. Now we would start this problem off just like any other unit conversion problem. We would start with a 2-row table. So you see I have a 2-row table drawn here. There is a small difference right here in this kind of first step. And the difference is you're going to have something in the denominator. Before, when you thought about all of the previous unit conversions that we did, we just started with something in the numerator. Here you're going to have something in the denominator. Remember what density is. It's a mass per volume. Think about that per. That per means division. And what you have to be careful of is right here in this very first step that you will have something in the denominator and it will be that volume unit. So here's the first place an error can occur in the problem compared to what you've been doing previously is not getting the starting information incorrectly. The mistakes that get made is sometimes people put all the information in the numerator. That's not where it goes. Your information that's provided for you has to match the way you have it set up in this dimensional analysis 2-row table. So the correct way of doing that is the mass part goes in the numerator, the volume part in the denominator. 6.23 ounces per every cup, per 1 cup. You're going to have something starting in the denominator here. And this encodes it correctly, because remember, our long horizontal line in our dimensional analysis is a division, is a per. Just like in the density, you have mass per volume. We're having that per, or that division, mean the exact same thing here. So that's why you need to start with something in the denominator. The same thing will go for your goal. Remember, we always want to write out our goal. Well, before you would just write out a goal in the numerator. Here, we're also going to have a denominator goal. Our goal is decigrams per milliliter. So what this really is this is really just two problems rolled into one. We're going to convert the ounces to decigrams, but we're also going to convert the cups to milliliters, all in the course of the same problem. Now, it doesn't matter what you start with. You could start with the mass, or you could start with the volume. It ultimately doesn't matter which one you choose to start with. We've kind of been trained when we've been doing math and we have numerators and denominators to kind of start looking at the numerator first. So that's where I'm going to start. I'm looking at converting ounces to decigrams. That's my first sequence of steps. So when we think about converting our ounces to our decigrams, again, we want to think, what units do we have in place? English or metric? Well, ounces we're familiar with. That's probably an English unit. Decigrams we're definitely not as familiar with. That's going to be a metric unit. So remember, anytime you're bridging the two gaps between English and metric, you want to first identify what is that key conversion. What is that translator equality that can speak and convert between English and metric? So let's look and identify that first. 16 ounces equals 1 pound. Well, that's not it. Those are both English units. 2.2 pounds equals 1 kilogram. There it is. So this one highlighted in green, this is our key translator equality. This is what's going to move us back and forth between English and metric. I know I have to use that. Well, before I can use that, the English part of that translator equality is pounds. Where am I starting with? Well, I'm starting with ounces. So it's giving me a hint of what to start with. Can I convert ounces to pounds? And the answer is, sure, I can convert ounces to pounds. So English to English conversion, that's been provided for. 16 ounces equals 1 pound. I just need to use that. I want the ounces to go away, so I'm going to put the ounces in the denominator. I'm going to put the pounds in the numerator. We can see ounces in the numerator and ounces in the denominator. Those ounces will end up being canceled to leave us with pounds. Now we're going to continue this on the next slide. On the next slide, we already canceled off the ounces. Now we have pounds. Now we can use that key translator equality that we identified. We identified 2.2 pounds equals 1 kilogram as the key way of getting between the English and the metric. Now I have pounds. I can use that. So in order to use that, I'm just going to go ahead and use it as is. I want the pounds to cancel. I'm going to place the pounds in the denominator and put the kilograms, because I want to go to metric, in that numerator. So pounds is going to go in the denominator, kilograms in the numerator, and that sets us up to have our pounds cancel off again for us. So we'll get our pounds canceled off. Now we have our pounds canceled off. So now we're in kilograms. So now we're in a good shape. We're in metric. That's good, but are we in the right metric? Well, not quite yet, because we look over for our goal all the way on the right-hand side. We have decigrams. We're at kilograms. So remember, here's another case where we're going from one metric prefix to another metric prefix. We're trying to go from kilograms to decigrams. Remember, unless you are very, very comfortable with your metric system, very, very comfortable, I do not recommend doing this in one step. Instead, do it in 2 steps. First, get rid of any prefixes, so we'll go to grams, and then from grams go to the new prefix. 2 steps is much, much safer for that. So kind of in this middle sequence of steps is kind of go where we're at. We canceled off ounces. We canceled off pounds. Cups we're leaving alone. We haven't touched that yet. Leave that be there. We will get back to that when we're ready to deal with it. So we want to go to grams. So we need to know, how can we get from kilograms to grams? This conversion is not going to be provided for you. This comes from knowing what those metric prefixes mean. So the relationship between kilograms and grams is that 1,000 grams equals 1 kilogram. So now we're using that. What do we want to get rid of? We want to get rid of our kilograms. We started with kilograms in the numerator. So that means the way I need to write this equality as a ratio is to get the kilograms in the denominator. That way they'll cancel, leaving the grams in the numerator. With that, we're able to cancel off our kilograms now. So being able to cancel off our kilograms, so we can get those canceled. Kilograms will now cancel. Where are we at? We're at grams. Now we can go to decigrams in our next step. So I'm trying to go from grams to decigrams. Again, this is another metric to metric conversion. So being this is metric to metric, those aren't provided for you. That comes from knowing what these metric prefixes mean. So we need to come up with for ourselves the equality that relates grams and decigrams to each other. For this one, there's a couple different ways we could write that. One way we could represent that is we could say that there are 10 decigrams in every gram. 10 decigrams equals 1 gram. Or another way of representing this is we could say that 1 decigram equals 0.1 grams. Again, use the one that makes the most sense to you. Use the one you're more comfortable with. We've been kind of consistently, for the examples we've done, using the one that doesn't involve decimals. So let's go ahead and continue that kind of pattern. I'm going to use 10 decigrams equals 1 gram. But if you see it as 1 decigram equals 0.1 grams, you want to make sure you do it that way. Do it the way that you end up seeing it a little bit easier. We just kind of go back and cross off where we've been and what we've done. Ounces have canceled. Pounds have canceled. Kilograms have canceled. Grams will cancel now because we're going to put the decigrams in the numerator because that's what we want to be left with. Grams in the denominator such that they cancel with our grams in the numerator. We kind of look and see where we're done, how we're doing, and we're in good shape. We're in good shape because we're seeing we have decigrams as our unit in the numerator. We look all the way over to the right, we're seeing decigrams in the denominator. That's our clue that, hey, we're on the right track here. Now, in this problem, we said there's a couple places where you can kind of, it's a little bit different than what some of the other unit conversions, the other dimensional analysis problems you've been doing. We recognize one of those at the beginning that, hey, we have something in the denominator. The second place you can sometimes make an error in these type of problems is right at this point. It's very easy. You see, oh, I have decigrams, I have decigrams, I have what I want, and saying, oh, I'm done. Well, you're actually not done yet. The reason why you're not done is, look, have all your units canceled? Well, not quite, because look in that bottom left. What do I have? I have cups. Now look all the way to the right. What do I want those cups to become? Milliliters. I haven't done that work yet. I've converted cups. I have not converted cups to milliliters yet. So I'm not done yet. In fact, we're only about halfway done with this problem. We took care of the mass. We successfully converted ounces to decigrams, but what we've not done yet is the cups to the milliliters. So we're not finished yet. We still have more work to do on that. We're going to do that part on the next slide. So first line is just kind of rehashing where we've been, and we can see where we've done, what we've done. where we're at and what we still need to accomplish. Remember, our ounces have canceled, our pounds have canceled, our kilograms have canceled, our grams have canceled. Now we're at the stage of trying to make these cups in the milliliters. And just like before, if you go back a couple slides, you would go and you would see, okay, now I want to work on these volume conversions. Again, cups is English, milliliters is metric. So I need to find that appropriate conversion, that translator equality. Well, that translator equality is quarts and milliliters. 1 quart, 946 milliliters. Well, I'm not in quarts yet. I'm in cups. Remember, where am I currently at? Where we're currently at, kind of highlighting this in yellow right now, where we're currently at is we're in cups. That's where we're at. Well, I need to get to quarts. Can I do that? Yes. That English to English conversion that was provided. 4 cups, 1 quart. Here's another spot where you can make an error. And this just kind of comes from, the repetition. We've been used to the unit we want to have cancel. We're putting that in the denominator in the past. Well, why did we do that? Because what we were starting with was in the numerator. Here, we're kind of in the opposite scenario. What do we have? Our cups are in the denominator. So in order for the cups to cancel in this step, we need to make sure we put the cups in the numerator. That way they're going to cancel. Our cups are still going to cancel. It doesn't matter if they're far apart. There's still 1 in the numerator, 1 in the denominator. Therefore, we started in the denominator. If I want to get rid of it, if I wanted to cancel, it had better go in the numerator. So I'm going to put the cups part in the numerator, the quarts part in the denominator. And again, we're going to now be able to cancel. If I just kind of quickly go through our old canceling again, ounces have canceled, pounds we took care of already, kilograms taken care of, grams taken care of. Now we're ready to cancel our cups. Cups in the denominator, cups in the numerator. Now they're canceled. Now where are we at? What do we have? We're currently at quarts. Well, we want to be at milliliters. Do we have a way of changing from quarts to milliliters? Yes, that was provided to us all the way at the beginning of the problem. 946 milliliters equals 1 quart. That was our translator equality that was provided. Well, now we're ready to use it. If we just go back and redo our old canceling a little bit darker, just to kind of re-show where we're at, we took care of ounces, we took care of pounds, kilograms taken care of, grams taken care of. Decigrams didn't. We wanted to leave those, and we did. Cups taken care of. Now I can use that quarts and milliliters conversion. I have quarts in the denominator, so where will the quarts have to go? That means in order to cancel, our quarts need to be in the numerator. That way they cancel with the quarts in the denominator. So I'm going to put the 1 quart of that conversion in the numerator. I'm going to put the milliliters in the denominator. What's that going to do? Well, that's going to allow our quarts to cancel. Quarts have now canceled. What do we have left? Well, we have left what we want to have left. Milliliters. That matches our goal. So we just kind of go back and look. All of our units have canceled except for 2. We kind of use purple arrows to point these out for us. The only things that haven't canceled have been our decigrams didn't cancel in the numerator, and milliliters have not canceled in the denominator. We look and we see what we want on each of these. We want in the numerator decigrams, and we want in the denominator milliliters. We're where we want to be on this. So this is set up correctly. Now just comes the mathematical steps. Remember, to actually do the calculation, any number you see in the numerator is a multiplication. Any number you see in the denominator is a division. So in order to calculate this out, how would we key this in? Well, across the top, we're multiplying 6.23 times 1,000 times 10 times 4. And now we're dividing across the bottom. Divided by 16, divided by 2.2, divided by 946. I'll kind of run through that calculation again. 6.23 times 1,000 times 10 times 4, divided by 16, divided by 2.2, divided by 946. And after you've done that calculation, you should get that our actual density is going to be 7.48 decigrams per milliliter. There's really not a whole lot new to these density unit conversions, these density dimensional analysis compared to what you've done before. It's all the same things. This is really just a combination of a mass and a volume one together at the same time. The only thing you have to be careful of is not stopping halfway. We talked about that. It's kind of very easy to forget that you haven't completed the whole thing yet. You're only halfway done, as well as remembering that when you first start the information, you're going to start with something in the denominator. When you're feeling comfortable with these types, that's your clue, that's your indication that you are definitely good on dimensional analysis. You know it, you're comfortable, and you're ready to handle any dimensional analysis problem that is ever thrown at you. We want to talk a little bit about specific gravity. We're not going to go into a lot of depth on specific gravity, but it's more of something you need to be made aware of. So when you hear specific gravity, what specific gravity is specific gravity is a way of expressing density in a unitless way. And this is done by comparing the density of a substance to the density of water. So water is our most common and important substance that we really have. So we can express density as kind of saying, how much more dense is this than water, or how much less dense is this than water? So the way we deal with specific gravity is sometimes abbreviated SG, is we take the density of the substance and then we just divide that by the density of water. It's comparing how dense is this compared to water. If we used our standard units of density, at least in the metric, it'd be grams per milliliter. So we'd have the density of our substance, grams per milliliter in the numerator. The denominator, we have the density of water, grams per milliliter. It's kind of useful for water. The density of water is 1 if you're in grams per milliliter. So that just kind of, you just have that numerator component. But you'd see, even though this is a kind of a complex fraction, if you have the same units in the numerator and the denominator, you recognize that these would cancel out. So that's what makes it a unitless property. It's kind of a comparison property. All units would cancel out for this. We're not going to do any specific problems with this, but this is more of something that you just need to be made aware of. Because sometimes in medicine and in healthcare, instead of dealing with density, you end up dealing with specific gravity instead. So where this sometimes comes up is things like blood analysis, urine analysis. They won't say the density of urine is such and such in grams per milliliter. They'll use specific gravity. The specific gravity of the urine was 1.04. Well, what does that mean? Well, that means it's 1.04 times more dense than water. You're just comparing that density to a standard. So I need you to be a little bit familiar with what specific gravity really is. I'm going to talk about a little bit about the 3 main temperature scales that we have: Fahrenheit, Celsius, and Kelvin. Now you can see the conversions that I have listed over on the left-hand part of the screen. If I write out those conversions, temperature in Kelvin is temperature in Celsius plus 273. To go from to go from Celsius to Fahrenheit. Degrees in Celsius is 5/9 times the Fahrenheit degrees minus 32, and you can see the Fahrenheit to Celsius conversion is kind of the opposite of that. I'm not so interested in you doing calculations with the conversions or memorizing those. That's just kind of doing math for math's sake. What I think is more important is that you understand the relationships that these different temperature scales have to each other. Because you could create your own temperature scale, but it's going to be used in relationship to other things. So what we're going to do is we're going to compare some things that we're very, very familiar with in order to kind of show similarities and differences between these three temperature scales. So the first thing I want to look at is that melting point of ice, or that freezing point of water. We know that on the Celsius scale, so I'm just going to highlight this kind of in the middle of the scale, that melting point of ice, where does ice melt at, or where does water freeze at? Well, we'll start with the temperature scales we're most familiar with. For Fahrenheit, we recognize that that's 32 degrees. Where does that happen at Celsius? At Celsius, that's 0 degrees. At Kelvin, where does that happen? That happens at 273. Now we're going to use this in relationship to something else that water does. We know that water can freeze. We also know that water can boil as well. So we're going to look at the boiling point of water. Now the boiling point of water in the Fahrenheit scale, 212. The boiling point of water on the Celsius scale, 100. Boiling point of water on the Kelvin scale, 373. So now right away by looking at this, we can already start comparing and contrasting the differences and similarities between Fahrenheit, Celsius, and Kelvin. Because we know water, whether their temperature scales existed or not, we know that water freezes, water boils. That's something water does regardless of what temperature scale we're measuring it in or working in. You can create your own with different numbers for each of these points. But we know that water freezes, water boils. So we can do some comparing and some contrasting with this. First thing we can look at is comparing and contrasting Celsius and Kelvin. If we look at Celsius and Kelvin, water froze at 0 Celsius, 273 Kelvin. It boiled at 100 Celsius, 373 Kelvin. So right away that tells us something. And what that tells us is Celsius and Kelvin have the same size units. It takes 100 units on each one of these scales to go from freezing of water to boiling of water. That means they have the same unit size. So that's the first thing we can kind of notice about that. The second thing we can notice is that Fahrenheit has a different unit size than Celsius or Kelvin has, and it's smaller. And here's how we can recognize that. We're going to compare again water freezing and water boiling. We said it took 100 units to get between those two different situations for water for Celsius or Kelvin. How many does it take for Fahrenheit? Well, for Fahrenheit, it takes 180. There's 180 units between where water freezes at and where water boils at. When we were looking at this for Celsius and Kelvin, how many units, how many little tick marks would you have over there? Only 100. What does that mean? Because it took 180 little tick marks on Fahrenheit, that means each little tick mark is smaller because it took more of them. So we can say that Fahrenheit has a different sized unit compared to Celsius and Kelvin. This also gets you a little bit at, again, we don't care so much. I'm not going to ask you to use these conversions, use these equations. That's math for doing math's sake. But if you understand the similarities and the differences between the temperature scales, if you were ever asked to do the math in some other point, you definitely could. But you can also understand now where that math comes from. You know, if we look at this conversion, Celsius and Kelvin plus 273, well, that's because they have the same unit size. They're just off by 273. The temperature in Celsius and Kelvin is always going to be different by 273. When you start looking at the Fahrenheit and the Celsius, you see this 5/9 or 9/5. Well, where's that coming from? Well, that comes from you have different unit sizes that you now have to somehow interrelate. So if we think about that, remember when we said there were 180 units on the Fahrenheit scale between freezing and boiling, and there were only 100 on the Celsius and Kelvin scale? So 180 divided by 100, well, you could reduce those down. If you reduce those down as far as you could go, 180 over 100, 9 over 5. Well, you kind of see that in the equation. You know, flip it around and look at it the other way. 100 divided by 80 would be 5 over 9. You're seeing those in those equations. So plus 32 versus minus 32, that just sets the 0 point. So now you're kind of understanding where these equations ultimately came from. They came from the fact that Celsius and Kelvin have the same unit size, but Fahrenheit has a different unit size. That's a little bit smaller. Some other things to notice. Here we're going to look at the temperature scales on the right. If we look all the way at the bottom, there is kind of a theoretical lowest temperature you can have. And that theoretical lowest temperature that you can have on Fahrenheit is minus 459. Celsius is minus 273. And in Kelvin, that temperature is 0. So this gives us another opportunity to do a little comparing and contrasting between Fahrenheit, Celsius, and Kelvin. Well, what can we say? Well, we see we can have negative numbers all up and down the scale for Fahrenheit and Celsius. We can see boiling point nitrogen, minus 196, minus 321. We're seeing we can have negative numbers. We can go below 0. So that's one of the other key kind of takeaway points. Fahrenheit and Celsius can give you negative values. It can be positive or negative temperatures. What about Kelvin, though? When we look over at Kelvin, the lowest temperature we can get, the lowest point on that scale is 0. That term absolute 0 that you may have heard of, that refers to that lowest point on the Kelvin scale. So Kelvin can't ever be negative. So here what you're seeing is some of the similarities and differences between Fahrenheit, Celsius, and Kelvin. So your four big takeaway points from comparing and contrasting these different temperature scales is that Celsius and Kelvin have the same unit size. Fahrenheit has a different unit size. For Fahrenheit, it's smaller. The units are smaller. We recognize that Fahrenheit and Celsius can give you negative values. Kelvin does not go negative. The lowest you could go is 0. So the last thing we want to talk about in this presentation is a little bit on energy units, because energy units come up quite a bit. And this is one of those things kind of like specific gravity. We're not going to do a lot of calculations with them, but it's more of something that you need to just be aware of because these are going to come up. So when we're talking about energy units, we're familiar with energy units. The one we're kind of probably most familiar with is calories. Calories are that English or that imperial energy unit. For metric, we have the joules. Although we're used to dealing with calories on our food labels, these are probably some of the most confusing units that are out there, especially in the English system. And even if you don't like the metric, this is going to help you see why metric is definitely superior in every possible way. And here's why. When you're dealing with calories, it actually matters whether the C in calorie is lowercase or capital. It'll have different meanings. I don't know about you, but that to me sounds pretty confusing. That when we look at that, lowercase versus capital has a meaning. Well, when we're writing C's, a big C looks a lot like a little c. Well, what if your handwriting kind of looks like a medium-sized C? Is that capital? Is that lowercase? That's like asking for trouble when you're using calories. And here's how calories actually work. There are 1,000 little c calories in one big C calorie. That's the conversion. It takes 1,000 little c calories to give you one big C calorie. When you look on your food labels and the items you're eating, the packaging, it often says based upon a 2,000 calorie diet. Well, those 2,000 calories are actually big C calories. If they were listing them in little c calories, well, if every big C calorie is 1,000 little c calories, then 2,000 big C calories would actually be 2 million little c calories. Kind of sounds gross to say, well, I eat 2 million calories a day. It's not actually incorrect if you're talking about little c calories. But that's one of those things. That makes calories kind of a strange unit. So this was recognized that this is kind of strange. The capitalization matters. So it's like the one time you'll see this not happen a lot. Sometimes they'll even mix metric prefixes in with English units. Usually we don't mix metric prefixes with English units, but in this case you will sometimes see that. The idea of a kcal, a kilocalorie. These are little c calories. So the same thing. 1 kcal is really 1,000 little c calories, which is the same as 1 big C calorie. So again, we're not going to do any conversions with this. You don't need to memorize these conversions. We're not going to do any calculations with this. I thought it was really important to show you what's going on with the energy, especially calories. When you're talking about healthcare, when you're talking about medicine, calories can play a role in what you may be discussing with a patient or a diagnosis. You really need to understand what those calorie units mean. And when you look at that, hopefully the slide really shows you that, boy, using these English energy units, especially the calories, is kind of strange. The capitalization matters. And to try to fix it, they sometimes throw metric prefixes in this. So, if you're not a believer in metric, that's okay. That's not how we've been brought up. But you can see some of the major problems with dealing with these English units is they're kind of confusing right from the onset with what kind of calorie are you actually talking about.